Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm pleased to introduce Jan Rabai. I hope I'm pronouncing that somewhat right. Jan is the Donald O. Peterson Distinguished Professor, very distinguished professor at Berkeley in the EECS department. He's very well known for his work in VLSI. I've authored one of the textbooks in the field. His current research interests include next-generation integrated wireless systems, and he is the co-director of the Berkeley Wireless Research Center, as well as the director of the GSRC, the GigaScale Systems Research Center. So, Jan.
Thank you. Thank you, Rich. So what we're going to do this afternoon is actually a sequence of two talks. What I would like to do first is, since I imagine that most of you are not very familiar with what GSRC stands for, or GigaScale Systems Research Center stands for. So I'm going to give you somewhat of an overview of the different activities in the center. And then I'll pass the baton to John Wozniak, who's going to talk about one particular project called RAMP, where he's going to go a little bit more in detail. So, but this is really an overview talk. And I titled it Electronic Systems Design in the Late and Post-Silicon Era. Now, if you look at the ITRS roadmap, 2003-2005, a couple of things we learned quite quickly. Number one is that looking up to the year 2018, things still look pretty healthy. It seems like that we should be able to keep on scaling CMOS or MOS, and that from a pure technology perspective, there's no real barriers or no real absolute no-nos that tell us that we cannot go there. So for the next 15 years, I think MOS still has an interesting roadmap ahead of us. But at the same time, we also know there's quite a bit of potential roadblocks that make it harder, some of them being economic, other ones being pure technologically. And there's some things like energy, for instance, which has been worrying us for the last 10 years. We've found some stopgap measures, but obviously it's not something that has gone away. We're going to have to keep on worrying about power and energy for the next 10 years. Other things have become also more and more outspoken. Challenges such as variability, interconnect delay, all those other factors start to play and come into the game. So if you really want to get to this year 2018, there's clearly some things we still have to be resolving. And I'm just going to give you some examples. Complexity is one. Chips of billions of transistors, non-trivial to design, and obviously you worry about time to market. If you have things which are so complex, can I bring those things out in a feasible amount of time? And we know, for instance, that the design effort is a clear and very strong function of the number of gates or the complexity. As I already mentioned, power and energy is something that's a very factor. If I look at the roadmap and I plot out, for instance, how power density, active power density is going to increase or evolve over the next 10 years, we see that it's still going to go up. And actually it's going to accelerate again. It slowed down a little bit in the 1990s, early 2000s. We're accelerating it again because voltage scaling, which we have been doing for the last number of years, actually is slowing down. We cannot keep on scaling down supply voltages. And even worse, leakage power density is going up even faster. Devices are getting lousier and lousier, start leaking more and more. They're not ideal switches anymore. Reliability is impacted as well for a set of reasons. If you do low power design, you start squeezing down on supply voltages, you reduce noise margins. And as a result of that, we're getting more sensitive to a variety of things, such as crosstalk. We're getting more sensitive to variability. We're getting more sensitive to one-time offsets, like soft errors and so on and so forth. So they all play together, but obviously reliability, making sure that our hardware works correctly, is a challenge. And if you look at all those things, and you start looking at solutions, you see that a lot of the assumptions we have made for a long time, and the way we have done design for a long time, might be challenged. And we might have to think about different ways of doing computing. So, The GSRC is one of the Markov centers, and I'll go in a second through that. GSRC answer to all those things is, yes, these are all interesting challenges, and you can address them in many different ways. Obviously, you have our technologists and our device guys coming up with new devices, better devices, or novel ways of manufacturing things. We have nanotube transistors, we have FinFET devices, we have all those things. We can come up with different circuit strategies. But overall, I believe that the most effective way of addressing a bunch of the challenges I just outlined is really looking at the system level, is system level solutions. Obviously, in collaboration with all the other things that are going on. You say the impact of a system level solution very often is much larger than tinkering at the lower levels. So here's our answer to the big challenges that are out there. Number one, I think we're going for an era of abundance. Means that we're getting lots and lots of transistors. And that's billions of transistors on a chip. So what we should start thinking about is, can I use some of those transistors to make our designs work better? Okay, so using the massive redundancy of transistor or the number of transistors we have on the die to basically make things work. Number two is self-healing. As I mentioned, chips basically are going to become less and less unreliable. Maybe there's a way for, rather than us making them work correctly, let the chips themselves use that abundance of transistors to make the chips work correctly. Resiliency, very important. Failures will happen. There's no doubt about it. A correct chip will be harder and harder to design, and over time failures will hit. So we have to think about designs that are resilient to errors and failures. And finally, I think we're going to have to play some of the statistics. The idea that a design is a purely deterministic thing is going to be over, and we're going to have to play with some of the statistics and the distributions of the device we end up with. So a brief history of GSRC. GSRC as a center was founded in 1999 as one of the first two SIA Markov centers. It was called initially the GigaScale Systems Research Center. And its main focus was on the development and design of test tools and methodologies to address the productivity crisis. At that point in time, late 99, these people say, gee, we're going to have chips with 1 billion transistors. And you look at the productivity increase for a single designer, and you see that the back gap is widening. Or as a result of that, for every chip, we're going to need more and more and more designers, which is going to increase the design time and the time to market. So that was the key reason behind the setup of the GigaScale Systems Research Center. And Richard Newton, at that point in time, was the managing director. We had a major change in focus in 2003, where at that point in time, a number of new centers came into action. There was an interconnect center, but they also added a device center, and a circuit center, and one looking at nanotechnologies. And we felt that from a pure partitioning perspective, pure system level type of a focus would be the better and more effective way of addressing this. So focus on system level solution to the main roadblocks in the ITRS. And as I said, there's 4 other centers that compete to complete Markov portfolio. Yes?
Markov is an acronym, right? Could you expand it?
Yes, in Microelectronic Advanced Research Corporation, and it's a subsidiary of SRC, the Semiconductor Research Corporation.
Yes.
Okay.
It's the legal arm of the Focus Center.
That's correct.
And the next question is, who pays?
It's
Industry and government is about a 50-50
50-50
split right now.
50-50.
The DoD specifically and our industry members.
It has evolved a bit over time. Initially, it was like 75% semiconductor companies, 25% DoD. Over the years, it has gone to more 50-50 model.
Got it.
Because the industry paying more, or shrunk, or the government's paying more?
Because actually more centers.
Paying more, actually. Yeah.
It has been more centers, overall increasing portfolio. Mm-hmm. So those centers, to be clear, those centers are multi-university centers. So they're virtual in the sense that you have one lead university. In this case, for GSRC, it is Berkeley. But we have 16 other campuses we're working with. The idea is to bring together, we believe, the best faculty in a particular area and make them work together. It's a very collaborative model, which is, I think, is an interesting...
The director has to learn how to herd cats.
That's exactly right. If you want to, I have a wonderful movie on that I show occasionally, the Herding Cats movie. I said, this is what it is like to run a center. But actually, I must say, it actually has been a wonderful experience. Bringing faculty together on a regular basis, We have 4 meetings per year, and put them in the same room to think about problems actually has been very, I think has changed the mentality. Nowadays our faculty get together and they have ideas, they start talking about it right away, rather than thinking about, gee, I'm going to publish it first and then I'm going to talk about it. So it's early disclosure. The other thing that has happened is by setting a overall vision as a center, people kind of start walking. They still don't walk exactly in the same direction, but there's some sense of direction that basically emerges. So the herding cat hasn't been proven that hard as I thought it would be. So the good news is we just got new funding renewed September 2006, so we're basically up and running again 2009. So here's our solution to what we believe the system level solution is to the big challenges of the IT-Res roadmap. I think what we see happening now and that's kind of covering the whole industry, semiconductor industry, is that concurrency is something that has emerged and is going to be with us to stay. It emerged initially in a more application-specific space, but generally, but slowly but surely, it has now also gone to general-purpose computing. And it brings with it some challenges, because my claim in general, it's easier to design a concurrent chip than to program it, or to make it do something, as some people have experienced. A little bit down in the future, further down in the future, I think resiliency is going to be the biggest bottleneck we have to address. And coming up with clever ways to make chips really resilient, or applications really resilient, is absolutely essential. And then we're going down to the 2015, 2018s. You will see a whole set of new devices emerge. Like as I mentioned already, carbon nanotube transistors and things like that, where the resiliency will be so low, or where the chance of having correct computation continues will be so low that we're going to be forced to rethink the computational models we deal with. So I call it the alternative theme. And behind that is the whole idea is the theory of doing basically this building complex systems. So these are kind of the 4 pillars we built the center on. This is how it's structured. We have a number of leaders in each space, and some of them you might be very familiar with. Wenmei Wu is leading our concurrent effort from Illinois. Todd Austin, who was giving here a presentation this morning, is leading the resiliency effort. Naresh Shamba from Illinois' information theory background is doing the alternative, and Alberto Sangiovanni Vincentelli is working on the core framework, the theory of system design. So let me briefly describe each of the efforts and just give you some examples of what we're after. So, design technologies for concurrent systems. So our belief is today you have 2 cores, 5 cores, IBM cell, 8 plus 1 is 9 cores on the die. Picture clear is that if you extrapolate it, we're going to have 100 to 2,000 processors on a chip. They might be homogeneous, they might be heterogeneous, but it's clearly something that's happening. And the main reason for that is very simple, it's power, it's energy. The fact that we saw we were hitting that power wall, in order to get to keep on the computational complexity to grow, we have to deal, basically making chips clock faster and faster just doesn't work. So we're going to a model that actually was kind of invented in early 1990s. It's better off, you're better from a computational efficiency, you're better off running n processors slow than one processor real fast. That's a great idea, but obviously it comes with some challenges. Because how, as I already mentioned, it's easy to design them, how do you program them, and how do you make it, how do you create an environment where it's easy to make those things, actually the software and the hardware, to interact with each other. So big questions. What is a better architecture from an energy efficiency, a resiliency, and so on and so forth? What is better to scale in the nanoscale? Big questions. Yes?
So we've heard this story from virtually all of our semiconductor friends. And it occurred to me that if you sit and look at P equals CV squared over 2 quite carefully, and you look at the scaling laws, you find that, I mean, what we're told is we can build in order short pipe cores that are just as fast as today's superscalar, and they're smaller, and they draw less power. And so we look around and we say, and therefore we're going to give you a lot of them on one die.
That's right.
And I look at that equation and I say, now wait a minute, guys, there's another answer. What if we just said thanks but no thanks? we'll take the cheap rather than the big.
Mm-hmm.
You mean
What do
a
you
small
mean by cheap?
number of efficient cores?
That's right. We'll just take the efficient core. And you know, after all, for most of the stuff that we do
Sure.
on the business desktop,
Mhm.
the computers are fast enough.
Yeah.
So what would happen if we just said thanks but no thanks?
It's a very good question, and it's a question that actually haunts the semiconductor industry today. I see already a set of companies that say, why in the world should I scale? It's happened originally in the mixed signal space. You can look at companies like National, recently companies like Cypress, and so on and so forth. More and more start saying, for the applications that we're thinking about, we're okay. Now, it's an interesting proposition, but it's a dangerous one. Because if I can come up with a solution
If you can do it and we
that's
can't, then we're in
cheaper,
deep shit.
it's a cost. It's all a cost issue. Can I give the same functionality for a cheaper cost, right? Or do I need a lot more functionality? That's the other thing, because the desktop does certain things. Hey, the evolution of the desktop or the laptop or whatever might suddenly require a huge amount of more computational power.
Yeah, we actually look at that very carefully. I mean, we've been energized about this just because of what we've understood this problem for several years.
That's right.
And it's right at the focus of our spotlight. But it's a very hard problem figuring out how to actually harness that stuff.
Absolutely. Absolutely.
And it has occurred to some of us that, well, maybe we should just concentrate on less expense, because that's another way.
Absolutely.
You know, if you want to spread computing into, for instance, the developing economies, they don't need Pentium 4s with overclock graphics and all of that. What they need is inexpensive and low energy.
Yeah, I see a clear bifurcation, or I call it the bifurcation of the market into different directions, where you will see very cheap devices, throwaway devices, very low cost devices. Scaling still can help you there to reduce the cost. It's still
the same. You could have said the same thing years ago. You look at just Moore's law scaling, and you could say, okay, rather than use those extra transistors for out of order superscaledness, why not just make a smaller die that's cheaper? That didn't happen, right? Because
It didn't
because
happen.
the market demands more.
Well,
market competition
I have
demands more
theories
function.
about that you and I can discuss offline sometime.
But
I think that computing actually came to a fork in the road back in the late 70s. And we went down one path and lopped off another path that we haven't gone down at all. And it might have been a better path. And I think I understand why we went this way. And now we're reaping the bitter oats that we sowed.
yeah,
right?
absolutely. But my other perspective, this is one side, it's cheaper. I still believe that there's a set of applications waiting basically for that massive amount of computation at a reduced
I
cost.
think there are probably quite a few.
Absolutely. So, and we talked about one with the design driver type thing, if universal connectivity. But if you look at it, and then you have the infrastructure space, the routers in the backbone, you have the big data centers and all this kind of thing. So, but all of them need their own particular parts, and you're totally right. They might require different answers, right? But again, though, I think even if you look at even your portable devices, you look at your cell phones of today, the small devices, those things are becoming more and more concurrent. Any one of those chips, you take a Wi-Fi chipset, there's probably going to be 3 or 4 processors in there today, and there's going to be more of them in the years to come. So concurrency, to me, is a given factor, and it's something we have to learn how to deal with more effectively. And as you've seen those slides, many people think it's true. Now, an interesting part on this slide is that this is from Shikhar Borkar at Intel, where they compare it. So what happens, 12 cores, 48 cores, 144 cores, and they say, yeah, for some applications, actually the 144 cores are the better choice. If I have lots of concurrency, this works better. If you don't have much, you're better off with the 12 cores. So it's really depending upon the workloads you're considering and what you're basically targeting. It's going to impact what architecture works basically the best. So what do we do with GSRC is actually what I felt is the only way to tackle this is not by having just pure software guys looking at it or micro-architects playing around with it or hardware people. But I think it's actually the better choice is to have a group of people coming from network on a chip, energy efficiency type of considerations, and bring them together with some of our top-notch compiler, operating system, and so on and so forth people. So this is a grouping which is very diverse. If you look at the names in there, really top-notch market architects together with software compilers, with hardware, network on a chip, and so on and so forth, power efficiency type of space. And let's see what they can do together. You've seen this work before. We have actually two philosophies sitting kind of competing with each other within the center. On one side, you have the group like Wenmei Wu. Wenmei believes in traditional legacy codes. It's like, C code has been doing this for a long time. We know how to write it. We know how to deal with it. So this is where a massive amount of code is going to be written. And so what we should do is a much better job at trying to parallelize this thing. That's been his lifeblood, and for the last couple of years, he's been spending quite a bit of effort in that particular area. Take code, analyze the dependencies, take away anything which is a false control dependency, and take the code apart, spend a lot of compute power on analyzing sequential versus concurrent node. And he has been quite successful. He's been showing that, I can take code like MPEG coders and things like that, which we consider as being massively parallel, but if you take them in a traditional compiler, not much concurrency comes out of there, or you write in C code. However, by actually doing a variety of transformations, combined with this deep analysis, and step-by-step combining this together, we see that we've gone from virtually completely sequential code to code which is now, today, automatically can be compiled. White means concurrent, gray means partially concurrent, means concurrent within the loop, but not over loop boundaries. Black means basically sequential. So that's where we're at today. We take an MPEG code core and bingo, we can actually go quite a long distance in parallelizing it. This is where we want to be heading. Wenmei believes that in 2 years he should be able to take virtually the whole thing and turn it into concurrent code. So that's one philosophy. And I think it's a useful one because there's a lot of legacy code. But at the same time, the other option says, well, gee, if things are concurrency is explicit, why not express it? Why not use languages that are good in making concurrency explicit and provide the tools to grab it and then translate it into processor architectures, either application-specific, configurable, and so on and so forth. So that's the second corner of the game. And we have both of them. And actually, I believe that both of them are right. There are certain things which are naturally expressed in a very concurrent type of format. A lot of the signal processing, a lot of the user interface type of things are more easily captured in that space. Other ones, like a lot of the legacy code that's out there, is better in a traditional sequential mode. So this is the Mescal environment, for instance, which allows us to think like, for instance, one application area went after is network processing. You take languages like Click and so on and so forth, explicit concurrency, we can take it in, analyze it, optimize it, and actually generate process or map it into processes like the Intel and XP processor and so on and so forth fairly automatically. So one of the questions that emerged, and I'm going to just jump over this, question is now, that's really nice. There's a lot of things we can do in this particular space by putting people together, but how do we analyze what is possible? How can we basically compare results? How can we provide a common test bed so that different researchers in the space can actually come together, share results, exchange results, and actually metricize progress? If you don't have the concurrent machines there yet, it's kind of the chicken and egg problem. So that's where the idea of the RAMP project came along. It says, well, actually, we can build those massively parallel machines today. If we just use boards with FPGAs, we can do it today. And I'm just going to cut here because I'm still in the tender from John's talk later on, where he's going to talk about what's going on with RAMP. But one thing I would like to point out is that since we basically started broadcasting this idea of having a common test bed for playing around in the virtual architectural space, something that allows us to build machines with lots of parallel type of processing units, we got a tremendous type of response in the academic community. From virtually every university in the country has said, hey, this is wonderful. So can we get one of those boards? Can we get one of those systems? Can we start helping basically participate in your community? And I think this might create something which is similar to what we saw in the 80s. When we started with VLSI, a bunch of universities working together, John Oosterhout and all these people creating CAD tools, sharing them, people developed libraries, and suddenly VLSI happened. because a lot of people kind of sharing results and ideas. I hope the same thing can happen as a result of this project. Okay, brings me to the next step. Concurrency is something we have to solve today. The 2-core processors are here, 4-core processors are going to be there tomorrow. We have to deal with it, otherwise we're going to go into a big crisis. Resiliency is something which is a little bit further out, but it's not that far out either. Think about 95 nanometers. I already see quite a bit of challenges emerging. You talk about 65, it's getting more outspoken, definitely variability. Talk about 45 nanometers, reliability, resiliency against errors is going to be absolutely important. So the target of this group is to think about post 35 nanometer technologies, so it's a little bit far out, that allow you to deal with about 99% transient hard silicon fault coverage without having to make your chip triple modular redundant. So dealing with a fairly small amount of area overhead and still make our chips very resilient. Again, a very eclectic group of people with a variety of backgrounds, from signal processing, information theory, to microarchitecture and software. Two basic ideas we're going after, two kind of philosophies. The first approach, which we call the self-healing, I often calls also the idea of the meditative IC. The idea is the following thing, is that we know that chips are going to vary over time. They vary as a result of manufacturing. So during the manufacturing process, a single design is going to come out in a variety of ways. Parameters vary, thresholds vary, so the performance, power, and so on and so forth is going to change. But that's not only throughout manufacturing time, chips actually also change over runtime because of temperature variations, temperature gradients, things like aging effects, voltage effects, and so on and so forth can cause a chip to vary in its performance with different time constants. Sometimes it's very fast, like a very short period of time. Some things take years to develop, like for instance some of the aging effects. So now, anything that basically on there can be measured. Actually, putting sensors on a chip to measure those changes is actually not too hard to do. A temperature sensor doesn't cost virtually anything, and most microprocessors today have them already on the board. The FPGAs have them too. But it's also possible to put sensors on there that measure leakage, performance, threshold, a whole bunch of parameters, noise, all those things can be measured. Now, something that can be measured very often, once you have to measure, you're on the first step to a healing process. The next thing you have to do is diagnostics. And once I have diagnostics, I probably can deal with some way to heal or cure the problem. So once I basically can measure the things, I can think about system-level intelligent control to reduce the stress. For instance, if a chip gets hot in a certain component, I might either throttle it, or if I have multiprocessors, I may move some of the functionality to another spot in such a way that I can cool things down. The other thing I can play around with is supply voltages. If something is slower, increasing the supply voltage will make it faster. If something is too leaky, I can reduce the supply voltage. So there's a set of knobs I can turn dynamically while the chip is running to make it address the problems. And ultimately, I might even do some other things like tuning and healing to alleviate reliability threats. For instance, there's some things, some aging effects, for instance, or some stress effects in chips that can be healed by just turning it off for a little bit. You just let it sit. When something is overstressed, you relax it a little bit, you let it hang out for a while, and then you take it back, it goes back to the old mode. So it becomes back to the old speed. If you can measure that, you basically can heal it. So, as I mentioned, sensors are quite easy to build, and people have shown a wide variety of them. People can measure noise on the supply rails, they can measure performance, leakage, temperature, and so on and so forth. And you even can monitor activity and predict it. You can predict activity on a chip as well. But if you monitor what's going on in a certain part, I can say, hey, this is going to happen, this is periodic, I know that basically some activity. Yes?
So, what is the OS technology that you're assuming it runs on top of RAM? Do you have a fixed OS, or are you allowed for different OSs?
This is a ramp-specific question?
Oh, yeah, okay, I'm sorry, yeah. Obviously, this doesn't have to do with ramp.
Now, ramp could... Obviously, ramp, obviously, the FPGAs we have today have very little controllability. That we can measure the temperature, and the only thing you really could do, you could think about realigning functionality. But John can answer this better. I don't think there's any particular choice yet about operating system for the ramp environment as we stand, right?
Yeah, our hope is it will run anything. Okay. What we actually do first is more of a matter of what's available to us, which I say we choose. I'll touch on some of that in my talk.
You're allowed to say the L word.
So what impact might these conditions have on the control logic that's making the decision to move things around and so on? Like, how do you prevent that itself from being factored?
Yeah. So the question is, if your sensors go wrong, well, or if your diagnostics component go wrong. Now, the key challenge always is a ratio factor. If I can have a chip where the diagnostic or the resilient part or the redundancy part is small compared to the rest of the die, then I can afford to harden that particular component, use wider transistors, make the thing more resilient in itself. And you can go one step further, but that's harder. You can even make those things a little bit more kind of better proof by not basically relying on pure binary decision diagram type of model, but something which is a little bit more kind of statistical based. So you can, that's actually bringing us to the third part of my talk, is the alternative computational models, where you try to get away without anything which has to be absolutely correct. But here you still assume that diagnostics unit has to be absolutely foolproof, or you basically run into trouble. Now, the big advantage of this approach is that is the following thing, is that with variability, what you get is the following thing, right? Is that the margins, typically the way we deal with variability in the past, you do always worst case design and you provide a certain margin. You make sure that for a certain yield, you get enough margin that you basically get enough parts coming through. If variability increases, what it basically means is that I have to increase my margins. I'm leaving more and more kind of crumbs on the table because I have to make sure that I can deal with variability in the clock as well as variability in the execution speed of my processing elements. Now, if I allow a module to be dynamically tuned, for instance, I have a chip, let's call this a processor. At startup time, I'm going to run a test program. I'm going to check what the particular performance of that processor module is. And then I can start tuning my knobs, my supply voltage, or my body biasing in such a way that I bring that block back within to the normal distribution that I would like to have. What you see is that you're moving away from worst case design and actually bring almost everything to nominal design perspective. Sometimes at a little at the cost of performance, sometimes at the cost of energy. But it brings the curves back in. And for certain cases, like this is for extreme low power design, this is subthreshold design, we saw that we actually had, for the same switching energy, we could increase the performance with a factor of 10 by just using dynamic tuning on the die. Just diagnostics followed by correction. And this is something we will see more and more. You start up a chip, and the first thing it's going to do is test itself and figure out where it sits in the overall execution space and dynamically adjust itself to fit within the specs. So here's an example of a project that's going on in Michigan right now. It's David Blau. We call it Elast-IC. It's actually a prototypal one of those meditative ICs. What it has is a whole bunch of processing elements. It's an array. It's fairly massively parallel with a variety of sensors. So there's an array of sensors distributed all over the die, measuring a variety of parameters. And all this information is then broadcasted to what is called this DAP. And that's the part that has to be absolutely robust. That's your diagnostic processor that determines what part of the die are performing well, which one are not performing well, and then can help you to try to schedule functions in such a way that you get fairly reliable execution. So it's a scheduler and management unit. In some sense, it becomes kind of an operating system. If you look at it, it's basically assigning tasks to particular components in such a way that you meet your. Yes?
Actually, that was motivated my question about the operating system. It seems like there has to be fairly tight integration with resource management here.
Absolutely. I think this is why, if I look at the grouping that I have in the Concurrent and the resiliency team, I say, hey, you have to have the hardware people talking to the operating system guys. They have to have enough hooks and connectors to uppers that they actually can observe what's going on and use that information in their scheduling and task assignment type of functionality.
So one of the things I noticed at ASPOS was there aren't a lot of sort of core operating system papers being published, research being done. Do you find that a problem in terms of trying to find collaborators on the OS side for this
Yes,
research?
absolutely. I think it's kind of amazing that this is something that I've been looking at. Says who are the kind of the key people who are going wild in this thing. It's a very small crowd. I think there's a lot of things that can be done by really bringing this hardware observability, transparency together with the management of the overall resource. And it's still a fairly small crowd. You're totally right. Okay, brings us to area resiliency. As I mentioned, if it's something is sick, you can basically try to help it for a little bit and get along. But if it gets too bad, it crashes. Right? You basically run into big problems. So we have to basically deal with system faults. It's no way to get around it. It's going to be things like one-time upsets, soft errors, and all these kind of things. But there's more fundamental things that things will fail because of crosstalk, because of the fact that we have bugs in the design. If you have billions of transistors, trying to get all the bugs out of there is impossible, both in the hardware and the software, and so on and so forth. So how to deal with that? Well, again, it's quite straightforward. From an overall high-level perspective, you need, first of all, error detection techniques. Checkers, testers, and so on and so forth. Then I have to do a diagnosis of what's wrong, and then do recovery. And obviously, all of those things have to work very nicely together. So the concepts themselves are simple. The execution is hard. Because obviously, error detection can be very expensive in itself. The question is, how can I make cheap error detection? Fault diagnosis is another big challenge. And you have to be able to pinpoint the error quite correctly. And then recovery is a trade-off. If the cost becomes too high, you might lose all the benefits. So trying to think about techniques of doing this in a methodological way is absolutely important. What we have today is a set of ad hoc things. And I really hope that out of the research, we see a number of things emerge that ultimately can lead to something which is methodology. Yes?
I have to put in a plug for my own work. So there's work that I did with Emory Berger from University of Massachusetts. We published in PLDI last year. The system's called Die Hard.
Right.
And it's at the software level, so pure software. Right. But I use replication and randomization to get these kind of effects. Right. And we have a follow-up paper that we submitted this year's PLDI. It's called Exterminator, and it actually goes beyond error tolerance to actually error repair. So it has all those features. Yeah. Absolutely. And I'm not making any claim that we're doing the only work in this space. Absolutely not. There's the whole community is being kind of energized around this topic. I think we have some very interesting things that have happened over the years. We have started developing some very interesting techniques. But absolutely, it is one of the crucial challenges. And the more research being done in this space, the better. Absolutely. And we have Ravi Iyer. Ravi, you know Ravi. Yeah, actually, one of his interns was a student of mine.
Yeah. So Ravi is doing a lot of stuff with us on the software type space. But at the same time, we also look at the hardware. I think you have to do both.
Yeah, I was going to say, it's almost always a full system.
So very quickly, because of time-wise, very quickly let me go to some examples. First thing that was done, that was described this morning by Todd Austin, was saying maybe I can build some cheap error resiliency at the circuit level. This is a system called Razor. It's a very simple error detector that allows you to reduce the supply voltage of your chip below the level that you typically should. So occasionally you're going to miss a timing edge. You're going to make an error. But by using the shadow latches here, we can detect the error, halt the machine, insert the bubble in the pipeline, and make it work correctly. So what you do is by what we call aggressively deploy, by pushing the supply voltage scaling faster or harder than we do, we save energy, but it costs, at the same time, there's some energy recovery cost. If you push it too hard, the energy recovery cost becomes too high, and you start losing. So there's an optimal voltage that we can find to execute a certain operation. So very simple error detection, very simple error recovery technique. You can do the same thing at the higher level. This is work at Illinois. Say if you do signal processing. Let's say this is an equalizer for a modem or something like that. Very often we do worst case design. You have to. You design your equalizer for the worst case channel you're going to deal with. Right? So what I can do again is saying, well, gee, what I'm going to do is this main block, which is fairly complex, a lot of computation, a lot of power, I'm going to scale this in supply voltage lower than I should. And most of the time it's going to do perfectly fine. So no problem. So I'm saving energy. But occasionally I'm making an error. Now, in signal processing, actually people have learned how to build estimators. So for most of the things, if I know the signals that are coming in, I can, in a cheap way, compute some bounds on where the actual result should be. This estimator is factor of 10, 20, 40 times simpler than the main block. So when you suddenly detect that your main block gives a result which is out of your bounds, you reject it, and you replace it by the estimated value. So what it does is reduce your signal-to-noise a bit from an overall output. You give up a little bit of signal-to-noise, but you save, once again, dynamically in terms of energy. So again, aggressive deployment. And here's an example of this thing at work. This is an error. This is an image encoded this way without basically voltage scaling. You push the supply voltage down and you start errors all over the place. And then I bring the correction technique in, and suddenly your image is almost as good as it was originally, with a slightly degraded signal-to-noise type of characteristic. This works in the space where you have an idea about where you can provide estimators, predictors, and so on and so forth, which is a lot of areas, actually, if you think about perceptual computing. Other thing that you can do, and that's emerging, is saying, well, gee, if we're going to have dynamic failures, today we do most of the verification task up front. We have static timing analyzers, we have verification tools, we have formal verification, all this type of things. One of the things that basically scaling brings us, as I already mentioned, is a lot of transistors. So why not use some of those transistors to basically do the thing dynamically? Bring verification on the chip. Have checkers running while your chip runs, looking at some formal properties, and when you detect them, you turn that basically into, you basically trigger a certain correction or a recovery type of strategy. And a couple of work that were done at Michigan, I'm not going to talk about this because Todd Austin talked about this morning. Remora checkers is a very simple checker running in parallel with the main processor to look at some properties and see if these are met. But we brought this now to a higher level, in hierarchy, basically start doing checking on multi-threading engines, where you have checkers that look at individual threads and try to prove and show that they are correct. And once you're correct, you don't have to worry about those things anymore. And then you have separate checkers that really check about the inter-thread dependencies. So a hierarchy of checkers. And in this way, we can avoid kind of the exponential complexity increase that you would get by flattening the whole thing out. So by putting hierarchy in here, we can create more complex checkers. But the bottom line is, I think, what you want to take away from this is that I believe that more and more of the functions we used to do up front, like test, verification, tuning, reliability, and all this type of thing checking, are going to move on the chip. I'm going to actually burn transistors to make sure that the chip does the right thing while running these things online. Okay, just to wrap this up, just a little bit more forward into the future, is that this is going to last to some point in time, but at some point in time it's going to get too bad. I think if you have chips, if I look at what's going on right now in the carbon nanotube transistor space, the chance that you're going to have all your gates working, I think, is about Zippo. It's actually smaller than zero. So you're going to have to think about other models of computation that are not basically purely based on the determinism anymore. And that's why we have a small effort. It's about 10-15% of our budget looking at this kind of more outrageous type of things and say, hey, maybe at least it's worthwhile to have a look at some of those type of things. And one theme, I'm not going to describe all of them. One effort that I think is quite interesting is extending the model that went from 1 processor to 1,000 processors. And I said, why not 1,000,000 processors? Or why not 1 billion processors on a chip? The idea of throwing lots and lots and lots and lots of very small components connected together with very dense networks, and let those things see if we can tackle particular problems with this type of network. So, 1,000,000 processors on a chip, very dense collaborative networks. A little bit, you might want to call it bio-inspired. The idea of having very small kernels, you have lots of them, very dense networks between them, very noisy channels, fairly high, fairly low signal-to-noise ratios, and so on and so forth, large failure ratios, makes you very often think about some of the bio type of models that people have been creating. And I think there's definitely some opportunity here into the long range. Just 2 examples. One project is an extension of what I just showed you. Remember the image processor? Large block, small estimator. I said, why not get rid of the large block altogether? Why not have n estimators? Let's say if I want to do motion estimation, why not have n lousy estimators of where the motion goes, rather than have one big block? and then have a fusion block in the middle, and that's the only place where you have to be actually quite correct. So each of those elements could make failures, might make errors, but the combination and the fact that you have redundancy on them can give you actually very good results. We call it the sensor network on a chip approach. Another thing that we're trying to do is look at things that might emerge by, for instance, massive integration of oscillators. Can I build radios that are absolutely robust by putting arrays of oscillators that lock together and create certain emerging patterns? Certain phase patterns that basically are controlled by the coupling between the different oscillators. Each of those oscillators can fail. A bunch of them can be quite inaccurate, but the resulting pattern that emerges is absolutely robust and allows us to transmit very well-known waveforms and transmission. So here's an idea we're playing around in. And what I would like to do with this thing is build actually a mechanical radio. A radio which is composed of purely mechanical resonators coupled together on a chip. No electronic component involved, so ultimately a low power. So for the sake of time, I'm going to skip over this part here. So kind of gives you an impression of what the center is all about, a set of ideas we're going after. If you want to learn more, we have a website that describes the different activities, the people involved, and so on and so forth. Lots of information definitely up front. Here's our 5 key core, the alternative, concurrent, core, resilient, and the design drivers, and a bunch of information. So if you're interested, please have a look at our website. So conclusion, I think that over the next decades, we will see design paradigms change quite dramatically. I'm very much convinced about that. We're not going to do design as usual. So variability and reliability will lead to new microarchitecture and computational models, and regularity and redundancy are really central tenets of things we have to go after. And what are the opportunity? Lots of transistors. That's number one. We have lots of transistors. Why not use some of those devices or a chunk of those devices to make sure that our chip yield 100% guaranteed? Whatever you do, they're always going to work. And the other one is the gradual incorporation of error-resilient computational models. Rethinking the traditional Boolean type of von Neumann-style models, I think, is a worthwhile thing to do these days. All right, thanks.
All right, thank you, Jan.
Sure.
So rather than take more questions now, I think we should actually move on to the
Yeah.
talk.
Yep.
We'll take questions at the end of the
Okay. I'll answer Jan's questions too. See if this non-Windows laptop works with your equipment here. Let's see, is there a phase? Can I switch the phase of this? Otherwise it's going to... There we go. It's going to wake up first. Okay. Well, thanks to Rich and Dan for inviting us up, and for Rich for arranging the visit. As you can see, I'm going to talk a little bit about the RAMP project. My name is here, but in fact, as you'll see, there's many contributors to this project, including Chuck Thacker, who's here in the room. So let me start with a little motivation. You've heard this story already from Jan, and you probably all know it. What we're seeing is a dramatic change in the way processors are being designed, to a large extent because of the power wall, but there's also a memory wall, and the combination of these two kind of lead to this brick wall in processor performance. You may not have seen this data before. This is from Hennessy and Patterson's new book, and it shows the spec-int performance of uniprocessors over the years, and since the days of RISC processors, performance was increasing at an annual rate of about 52% per year. And something happened a few years ago, and it kind of flattened out to about 20% per year. And this is primarily due to these limitations, power limitations, memory limitations. So there's really a sea change in processor design. Most people believe that this is going to lead to chip designs with multiple cores because, as Jan said, many smaller, simpler cores are more power efficient. This also leads to a very nice model for hardware scaling into the future. And so you might think that what Moore's law will be from here on out
is really doubling the number of processor cores or CPUs every couple of years. So you can see it doesn't take too long to get to hundreds or thousands of processors. Another way to look at this is my friend Dave Patterson put this together. So the Intel 4004 that came out first integrated microprocessor in 1971 had 2,312 transistors. This shown below it is the Berkeley RISC-II processor, the first kind of real implementation of a RISC processor. This was done at Berkeley before I was there. Patterson led it up. It had 40,000 transistors. If you scale the Berkeley RISC down to modern day 65 nanometer technology, add in FPU caches, you can fit exactly 2,312 of these RISC-II processors in a modern day die. So in fact, in some sense, we're replacing what was a transistor in 71 by a whole processor now in 2006.
You can't connect them to each other.
Well, yes, I know. But, well, actually, if you do the math, there's also room in here for some interconnect and some other things. So it sort of works out. But you get the point. So the problems, okay, so we see a sea change in the way processors will be designed. We'll be seeing hundreds, thousands of processor cores per die. The problem is algorithms, programming languages, compilers, operating systems, architectures, libraries really aren't ready for this. Also, history has kind of shown that software people really don't start working very hard until the hardware arrives. And once it does, then within a few months, they tell the hardware designers everything that's wrong. We wait another 4 years for a new turn on the hardware, and that really just slows things down. So the real question we asked is, how do we innovate in a timely fashion on 1,000 CPU systems for algorithms, compilers, OS, operating systems, without waiting many years between hardware generations? So that was the real kind of motivation behind the RAMP project. And the real vision then was, can we build sort of a time machine? Can we build a massively parallel processor today using FPGA technology? And it turns out that FPGA technology, if you haven't looked at it for a while, has really advanced quite a bit. Even these days, with modern technology, even a couple years old FPGA technology, it's possible to put probably 10 CPUs or more on a single FPGA, soft processors mapped into FPGA resources. Therefore, we could build 1,000 processors, 1,000 CPU system with 100 FPGAs, which is not a lot. It's a relatively modest volume. And in fact, we know from working with our friends at Xilinx that it's possible to put 16 32-bit simple soft RISC processors in the Vertex 2V Pro technology, which is a 2003 really FPGA technology. And the nice thing about FPGAs is that they're following Moore's law very nicely, in that every couple of years or year and a half, a new generation comes out, which is about twice as dense and about 1.5 times as fast. So the vision is the architecture research community, a collection of researchers from universities, are coming together to create an out-of-the-box, massively parallel processor that will run standard binaries and for operating systems and applications. So what we'll do is build what we call the gateware. This is the stuff that turns an FPGA into processors, which would be processor cores, caches, coherency engines, Ethernet interfaces, switches, routers, everything we need to make this massively parallel processor. And then, and we think we can do this kind of 1,000 processor-like system perhaps by the end of next year. It's kind of aggressive, but that's kind of what we're shooting for. And we'd hope to have some standard ISA binary compatibility, a 64-bit cache-coherent massively parallel processor, running at probably around 200 megahertz. Todd Osman was here this morning. He talked a little bit about his history doing Simple Scalar, and Simple Scalar was a very successful and a widely used piece of research infrastructure within the university and research lab community. It was a standard simulation platform for scalar processors. We hope that we can reproduce that kind of success and have a standard platform for parallel processing research, and also provide an early platform for software development. So we feel that we're kind of accelerating research in this area, and that's why we came up with this name, RAMP, because that's what it stands for. And also Berkeley has to have these 4-letter acronyms that begin with R, and this one fit nicely. So we hope also to create kind of a multiprocessor watering hole effect. RAMP can become a kind of a railing point for a lot of research associated with parallel processing. And this is kind of what Jan mentioned. A similar thing happened in the Berkeley tools for VLSI design. Got a lot of universities and research labs interested in working together, and there's a lot of synergy that happens from bringing different groups together. For instance, groups working on kind of internet in a box type internet scale computing could be done now in a very controlled environment, data center computing type systems, all kinds of work in reliability, router design, languages, compilers. And we hope that there'll be, by having this shared piece of infrastructure, there'll be lots of cross-disciplinary interactions in addition to innovation and architecture itself. Another way is kind of another kind of success is going back to the VAX and BSD. The VAX in the early 80s became the standard research platform for a lot of work in operating systems and languages due to the work at Berkeley and other places. So this is who we have involved. So this is the original set of participants. They're from 6 universities. I won't list them all, including at Berkeley, Dave Patterson, Jan, and myself, and I got cornered or roped into being the PI of the project, at least for a while. We're also working with Shilin Liu at Intel. The kind of hardware and a lot of the development is being centered at the Berkeley Wireless Research Lab. It's become part of the Marco GSRC Center that we've been talking about a little bit today. There's been a major commitment from Xilinx for the donation of FPGAs and some cash for building hardware prototypes for the developers. And of course, we're working quite closely with Chuck Thacker here at Microsoft Research. And what we're working on is the next generation hardware, the RAMP 2. I'll talk a little bit about RAMP 1 today. But with Chuck, we're doing the next version. And then we also have some collaboration with Sun and IBM, who are contributing processor cores and a little bit of cash for student support.
So how much is the machine do you anticipate sort of when you're done?
The current generation, the RAMP 1, which is built around this B2 platform, which I will describe, costs us around $10,000 per module. That's because we get donated FPGAs from Xilinx, but most universities can. Interesting size RAMP machine is probably 16 modules or so. So that gives you kind of an idea. I think what we're doing with the next generation that we're working on with Chuck is that the price is going to come down quite a bit because the FPGAs we're using are about as big as the current ones, but they're much cheaper now. So it will be more generally available and more generally cheap. But we're in that range of tens of thousands of dollars for a decent sized machine up to it's kind of it's all kind of computing by the yard. It depends on how many modules you want to buy, but it's in that $50,000 to $100,000 range probably for a good sized machine. But there's an awful lot you can do with a single module, as you'll see. Okay, so if you look at what's really important for this type of platform, for a research platform for multiple processors, not as an end user running jobs that run on massively parallel processors, but doing research in this field, the things that are important is that we want a machine that's scalable. We want it to be relatively cheap because of our funding situation, cheap to buy and cheap to operate. We want to have it in such a way we can build a kind of an open source or a community around this. We need lots of debugging and simplified debugging. We need it to be reconfigurable because we want to try many different parameters of the machine, many different variations of parallel processors. We have to be able to come up with credible results right? And the performance, interestingly enough, is not all that important. It has to be a high enough performance machine so it can run a standard software stack. But it doesn't have to be, speed is not our primary concern here. In fact, just about anything we do using FPGAs, we're going to have a huge performance advantage over a simulator, for instance. Right? And that's the main thing we're going to get here. Right? And this is really different than the priorities if you were building a parallel computer for real users with real applications. So in kind of a university tradition, we graded the alternatives, the various options available to building a research platform for massively parallel processors. And the alternatives we look at are SMP type machines, clusters, the software simulation, or this FPGA ramp approach. And it turns out for the other alternatives all have something that really kills it for us. In the case of the SMP machines, these are prohibitively expensive machines. Clusters, it's in the maintenance, the cost of ownership of these things. We have to pay staff to maintain these clusters of machines, and they take lots of room in our machine rooms and lots of power. Simulation has basically zero performance for thousands of processors. And for ramp, it scores fairly well in these metrics that are of interest to us, except, in fact, in all the metrics, except not so great in performance. We'll probably only get 100 megahertz or so processors instead of state-of-the-art 2 or 3 gigahertz. But once again, it doesn't really matter so much. Our jobs will run a little slower, but if we can do our experiments in hours or overnight, that will be sufficient. And FPGAs are getting faster all the time.
Everybody in this room can remember what it's like to compute on a 90 megahertz Pentium.
Yeah, that's right.
But it wasn't all that bad.
Yeah, it's not that bad.
1 megahertz Apple.
Yes.
Well, there's that. That was bad.
Right. Right. Okay, so that's kind of the motivation why we're going in this direction. The hardware we're using, the Ramp 1 hardware is based on this B2 platform, and I'll talk a little bit more about this and the history of this at the end if I have some extra time. This is a board that actually predated the Ramp project. This came out of some other work at the BWRC. This was completed in about 2004. It's a fairly large PC board, 14 inches by 17 inches, 22 layers. This one uses the Xilinx Vertex 2V Pro 70 technology, which is their 130 nanometer, 1.3 micron CMOS parts. You can see the 5 here, and there's 20 DDR2 DRAM banks. So we get a total of 20 gigabytes of memory on this board. There's some extra ports for maintenance and debugging, a lower speed Ethernet. There's a bunch of high speed ports. There's 18 10 gigabit per second communication ports off the edge of the board. And as I said before, this module costs, without FPGAs or DRAM, about $5,000 to produce. A little more once you put it in a power supply in a box. In more detail, it looks like this. The configuration of the design of the modules like this. There's a central FPGA that does a lot of debugging, housekeeping, runs Linux typically. The one property of these FPGAs that we use is that they have 2 hard PowerPC, Power 405 cores on each FPGA. They come in handy for things like running Linux, for booting the system, for maintenance. FPGAs are connected together, as you can see here, with these fairly high-speed onboard links. These were designed to run at about 300 megahertz DDR for about 5 gigabyte per second transfer between FPGAs. So there's a lot of interconnection between the FPGAs. The FPGAs, each one is surrounded by 4 DRAM banks. There's one DIMM module that plugs into each one here, and they're all independently addressed. So it's 4 independent address banks into the DRAM. And then there's these, we use the so-called MGTs, the high-speed SerDes type transceivers on the FPGAs. They get channel bound together to build out of each FPGA 4 10 gigabit per second links. These conform to InfiniBand or the 10 GigE standard. So these are used for connecting module to module or connecting to a commercial switch, a commercial 10 GigE switch, for instance. So this gives us a way to build scalable systems. You could start with a single module and then add more modules by plugging them together, either directly with these links or through commercial switches. So our plan then is to start with this hardware. What we've done is through a donation from Xilinx we've built a bunch of these modules and we've been distributing them to our collaborators, that group of 6 universities that you saw listed. And we're starting to build some ramp prototypes, and I'll talk about those in a minute. Our goal is to build and release a publicly available out-of-the-box massively parallel processor emulator. In fact, probably several different designs. And these will be the starting point for other people to do research. So they'll either be the platform on which people can do software research, or they'll be the starting point for more novel architecture research. So the idea of ramp really isn't to do architecture research per se. The idea is really to enable it. There's kind of a give and a take. We're all banding together and putting our resources into building this shared infrastructure, and then hopefully we're going to take something out of it later to help enable our own research. So if you talk to this group of 6 university collaborators, there's probably no common vision on what a massively parallel processor of the future should look like. There's some in the group that are really excited about doing cache coherent designs. There's others that are more behind massive passing machines. But we can all come together and work on a common infrastructure and make sure that it's general enough to handle all those different models. So what we're going to do is base our distribution on a standard instruction set architecture. And I'll talk a little bit more about that in a minute. And we'll make it complete with operating systems and libraries. And then, as I said, this can become the point of departure for a lot of different work. And hopefully this work will get turned back into the community in this kind of open source-like effort. The other thing we're doing simultaneously with this is designing the next generation of ramp hardware. Xilinx has come out recently, or has announced their latest Vertex, Vertex 5, which is 2 generations beyond what the B2 was built on. We'd like to take advantage of that, partly to get more density and partly to get cheaper boards. And then we hope, and part of this is to set up with a third party who can do the manufacturing and the distribution of the hardware. So it'll be as easy as anybody who wants to participate in ramp could then go and buy the hardware, download our software from our website, and then they're ready to go. We have been distributing B2 boards ourselves. Largely Ken has been kind of leading the effort, and it's a lot of work. We're really not set up at the university to be selling and distributing hardware. So we're anxious to work with a third party, and Chuck Thacker has been instrumental in helping set this up.
The main problem is for industrial people, you have no way to take a check.
Right. Our hope then is that this will be wildly successful, and then ramp 2, 3, and ramp 4 will just continue as new FPGAs come out, as our software base grows, as more people get involved in this. It'll kind of take on a life of its own. To help kind of get this started, we applied for and received a National Science Foundation computing research infrastructure grant, and this money came to Berkeley, where we hired one hardware kind of gateware person, and that's Dan Burke, and we have an open position right now for kind of an operating system and software person. So if you know anybody who wants to leave Microsoft to come to beautiful sunny Berkeley, we're looking for somebody. The other thing is we're also currently looking for more support for graduate students. We really don't have a big grant to fund our students. The GSRC is helping to support, but we're still could benefit from more industrial and agency support. Okay, so the question that came up early on in the project is which instruction set architecture to choose for building ramp. Our goal is ultimately to have RAMP be ISA agnostic, so somebody could plug in their own instruction set architecture. We could switch a Spark for a PowerPC or for possibly even an x86. And that's what we'd like to do. But we need to choose one to get started with. And what we have so far, we've been talking with lots of companies. We got Power 405 from IBM, various versions of Spark, including the Spark v9. Sun putting this in the public domain a few months ago had a lot to do with us bugging them to see if we could get their processor design. Of course, we have a Xilinx Microblaze, which is the Xilinx version of their RISC that runs quite nicely on FPGAs. We're likely to get a 64-bit IBM Power architecture at some point, and we're talking with ARM. There's others we could get. We think we could get the MIPS if we wanted it. It's unlikely that we can get an x86. We've been trying. We haven't found anybody who's willing to give us the synthesizable version of a x86 architecture. It's even less likely to get a 64-bit version. So one of the things we did was fairly carefully did an analysis of which cores were available to us to try to decide which core to use for moving forward. And I don't expect you to look at all the details here. You can go to our website and look at it. In fact, this goes on a bit more. But I wanted to point out a couple things. So we get processor cores from companies, for instance, the 405 from IBM and this Niagara core from Sun. But usually what you get when you get a synthesizable processor core is a VHDL or Verilog, a hardware description language version of processor core that was meant for verification or for something else. It isn't really appropriate for FPGA implementation. In fact, if you take those synthesizable cores and push them through the FPGA tools, you use lots of FPGA resources. And that's this column here that lists the LUT count. So these Vertex 2V Pro 70s FPGAs that we're currently using have about 70,000 LUTs, lookup tables, which is the basic logic unit within an FPGA. And most of these processor cores use quite a few of them, and they kind of blow our budget fairly quickly, except for a couple. And interestingly, the one from Xilinx, which was designed specifically to be efficient inside FPGAs, has a fairly modest number of LUTs, 2.8K out of our 70,000. In fact, it's less than that if you throw out it's about 1,000 LUTs for the processor and then another 1,000 plus by the time you put the floating point unit in and the bus interface. The other one that's fairly nice is this Leon core. This is an open source version of the Spark v8 architecture. So we're kind of putting our weight right now behind this Leon core for a while. In the meantime, we're working with our friends at IBM and Sun and other places to kind of do optimized versions of processor cores, the same ISA, but an implementation that's more efficient inside of FPGAs. And it's just a matter of remapping, doing some things by hand and optimizing. One of the things we are trying to solve in this project is these issues here. And there's this idea of hardware scripting. We're working with people all over the country contributing blocks. Somebody comes with a processor core, somebody else with a coherency engine, somebody else with a network interface. We'd like to be able to merge these together. And so there's kind of a distributed development model, and we need a way to pull together various designs and have pieces of designs and have them work together. So we need kind of like a hardware scripting concept. The other thing is that to save FPGA resources, it might be that some piece of our design actually takes multiple FPGA cycles in order to execute one target machine cycle. For instance, for emulating a very large L2 cache, and it doesn't fit inside the FPGA, we may need to use DRAM. It's going to take multiple cycles to go out to DRAM. We'd like the emulated processor to think that all happened in one cycle. Right? So this concept of time dilation. It's really what we're building here is a distributed event simulator. And time has to be explicit and managed and advanced at a very controlled rate in order to do cycle-accurate emulations of these systems. So that's the other issue we had to deal with. And then we also would like to hide the details of these FPGA emulation platforms to the developers, so they can worry about building the functionality of the components and gluing it together, and somehow our tools should map it or take care of the low-level details of how to communicate from FPGA to FPGA or how to communicate across those high-speed serial links. One of the things that is nice about doing this in this day and age rather than 15 years ago is that most of the large building blocks, processor cores, network interfaces, coherency engines, and the like, even though they're fairly large blocks, each one will fit entirely within an FPGA. We don't have to think about partitioning a component across multiple FPGAs. So this is a different problem than, let's say, QuickTurn, if you're familiar with them, had back years ago. They build logic emulators that take large designs and they distribute them on a number of FPGAs. But they have to partition things with many wires across FPGAs and quickly run out of bandwidth on the wires. Here, there's kind of a closure around our building blocks, and they fit all within FPGAs. So that's nice. So based on these ideas, we developed this thing called RDL, or the Ramp Description Language, which is a simple net listing language that defines a standard interface between modules. And it's really a way to provide the plumbing that plugs together components, or we call them units. And what the principles behind RDL are is that our design will be composed of a bunch of units, and these units are fairly large things like a CPU plus an L1 cache or a DRAM controller perhaps. And then they communicate through no buses but through point-to-point lossless channels, kind of FIFO-like channels. And the idea is that this works, these unit definitions, the functions can be written in any hardware description language such as Verilog or VHDL, even BlueSpec or C, could be in software modules. And what RDL does is hide the details of the communication by automatically mapping these channels onto the physical links that exist on the hardware platform. So they might be realized within an FPGA as just wires, or FPGA to FPGA, or board to board. And the other thing it does is it has a model for keeping track of time explicitly, and it advances target time based on the time of the inputs and how much time a unit takes to execute. So kind of like as I said before, like a distributed event simulator. Currently, we do that by communicating on every target clock cycle. Sometimes you send data, sometimes you send a null token. Another way to do it would be with timestamps. This basic model is similar to other things that people use, sort of it's a process network idea, really, similar to a CON process network. Except the difference here is that we explicitly manage target clock cycles. The nice thing about RDL, once we had it, in addition to solving those problems we set out to solve, there's some other things we get. For instance, since all the communication is over these channels, which are explicit, we can automatically insert monitors and debugging stuff into our designs. In fact, this works out really well in FPGAs because there's lots of gate resources around. We can build hardware monitors, all kinds of counters, checkers, and automatically, in some sense, instrument the user's design. Or it goes the other way. We can inject messages into the network so we have control over the communication. One of the things that's upcoming is building in activity counters that then can collect statistics that are used offline for power estimation. Okay, so quickly what I'm going to do is describe the three prototypes that we're working on. There's ramp red, ramp blue, and ramp white, and you'll see where these colors come from in a minute. And we kind of stage these in a way that we can have some early success and start showing some promise and start getting our hands dirty and building some real prototypes. The first one we got going was called Ramp Red, and it's centered at Stanford. This is, as far as we know, this is the first multiprocessor with hardware support for transactional memory. Right? And this kind of follows on a research project of Christos Kozirakis and team over there investigating transactional memory semantics. And what they did is take, within the ramp environment, This one uses the embedded PowerPC cores to keep things to get it up and running quickly, and it connects the PowerPC cores to a shared memory. They replace the standard cache with a special cache that implements the transactional memory semantics. And then there's a little proxy kernel that runs on each that forwards system calls and exceptions to the main Linux kernel that's running on the FPGA of the center FPGA of the processor and the center FPGA of the B2 board. So this whole one right now runs on a single B2 board. This was fully operational this last summer. And the nice thing about it is that with 100 megahertz PowerPC processors, this gives about 100x faster simulation than what they were getting in software on a 2 gigahertz workstation. Another prototype we're excited about is Ramp Blue, which is centered at Berkeley at the BWRC. This is a emulation of a class of message passing machines that primarily will run kind of scientific type code, MPI. We favor this thing called UPC, it's Unified Parallel C. This is a picture of the prototype that's in our lab. There's 8 of these B2 modules, each one inside one of these 2U chassis. They're plugged together. These light blue cables are the 10 gigabit per second links that connect the boards. Right now, the boards there's a direct connection from every board to every other board, a very simple topology. And there's another network, that dark blue one up on top, which is used for maintenance and for configuration of the machine. The applications we're running are the NAS parallel benchmarks. This is basically a bunch of scientific code. This one uses soft processors. Each FPGA holds 100 megahertz Xilinx microblaze soft cores. These are the 32-bit processors. Currently, we've mapped 8 processor cores per FPGA, and so for a total of 256 cores in this bank of 8 modules. Only about 40% of the FPGA LUTs are occupied on each FPGA, so we believe we can push this number up probably at least to 12. So each FPGA, in addition to those 8 processors, holds a gateware version, a soft network switch, shared memory controller, a shared double precision floating point unit, and shared console switch, which is kind of a debugging interface into the machine. So as of Sunday, 2 days ago, we were successfully running NAS, I think all of the NAS parallel benchmarks on 256 cores, which is a major milestone for us. So this kind of gets us experience in building big multi-core systems out of FPGAs. It's the first time I've seen anything like this done. The other prototype that we're just starting, here it is. It's called Ramp White, and this includes many universities, and that's why the color white. It's more of a longer-term effort and a little more ambitious. This one is going to be a distributed shared memory machine. It'll take components from the other ramps. It's being integrated at UT Austin. This one, we're going to use a simple ring-based network and ultimately a directory-based coherency engine. You can see how each processor connects to the ring. The initial implementation is using, again, the embedded PowerPC cores with a Snoopy cache. Later, we're going to plug in fairly soon, within a few months, we'll plug in the Leon Spark cores and a directory-based coherency scheme. So this one, along with the other 2, will be the reference designs that we make available to the community. They'll need to be cleaned up and documented, but that's kind of the work that we're doing over this next year. Okay, so here's a summary on the ramp stuff. So really, what we're trying to do with ramp, as I said, is build a system-level time machine. We really want to preview what machines of the future might look like and help accelerate us towards that future. The nice thing about FPGA platforms, one of the nice things is you can trace everything, we can reproduce things, we can tape out a new machine design every night if we wanted to. We can FTP machine designs across the network and try them on our own ramp versions. In fact, we can verify if the wild claims that are coming out of MIT are really true, and we can try their experiments on our machine by having this common platform. We think this is going to make a huge impact on massively parallel and distributed computing research. And as I said before, kind of witness to what impact this kind of thing could have. This simple scalar simulation program that Todd Austin wrote, it's been cited in more than 350 publications, and there's a whole generation of grad students that were trained on research using that simulation infrastructure. We feel like we really need to seize the day here. People need this capability. FPGA technology is ready to deliver. It's getting better all the time. We have platforms that are suitable already. And many groups have been working in this direction independently. In fact, that's why we all decided to join forces. There'd be discussions at the architecture conferences. And everybody had their own little FPGA project going on in the corner. And so it seems like a good idea to combine forces. Let me just put up names of some of the students and staff. And there's more information on the project at ramp.eecs.berkeley.edu. And that was all I wanted to say about ramp. I have a few more. Can we run over a little bit?
We can run over a little bit.
Okay. So I have a few more slides on more generally the background for this B2 platform and where it came out of BWRC. And this has to do with a larger effort to do work in reconfigurable systems. So let me just go back to B1. What B1 was the first Berkeley emulation engine. It was built on an earlier generation of FPGAs. This one was about a meter squared PCB, probably the biggest printed circuit board I ever saw, that had 20 Xilinx 2000E FPGAs on it and not much memory. It was designed at the time by Broderson and students as a platform for emulating ASICs. A lot of the work at the Berkeley Wireless Research Lab has to do with building custom integrated circuits for radios, and low power, high performance radios, and experimenting with new algorithms. The idea was if we had enough FPGAs in one place, we could, in the real system, run an emulation of the real chip before building it. And this shows a B1 board inside that box with all the fans connected to real radio front ends and radios, receivers, and transmitters. It's a very nice way to do chip emulation, is to emulate it in the context of its real use. The one really important thing about this development was that the work due to Broderson and students was to build a programming interface for this system, and actually so that people other than hardware designers could take advantage of this platform. Okay, and what it was a MATLAB Simulink-based tool flow, where there was a bunch of tools that would take Simulink diagrams, which is this graphical representation language, and automatically from that generate configuration files for the FPGAs. So the user really would see this and could get this running on the FPGAs. Another interesting thing about the project was that the tool flow simultaneously supported FPGAs and ASICs. So from one specification, you could go to an emulation and go down and push a different button and go down to a mask for generating ASICs. And this got me attracted to the project. I had been searching for a long time on programming models for FPGAs and reconfigurable devices. This was the first really successful one that I saw. It seemed to be the right combination of explicit representation of parallelism, high enough, simple enough, and abstract enough representation for people to be productive in. One of the interesting thing that happened, though, once this platform was built, it was built primarily for doing ASIC emulation, and it was very successful at that. But the thing was sitting in the lab, and other people started finding other uses for it other than just ASIC emulation. They saw it as a useful computing device in its own right, given this kind of programming interface, this Simulink programming environment, it was a simple thing for lots of people who are investigating algorithms and other computations to program it up on the B and get all kinds of acceleration. This is just one example of the kind of thing that happened. There's people in the lab studying these low-density parity codes. These have been widely studied. They've been proposed as error correction codes for Ethernet, among other communication standards. And one of the important things in these codes is understanding the noise floor of the codes. And this is usually determined by doing long computations and plotting the bit error rate as a function of the signal to noise ratio. And people look for a change in the slope of that to determine when the code kind of craps out and where the noise floor is. NEC was the first one to try to, so if you do this if you try to compute this on a workstation, you can get to about 10 to the 6th or 10 to the minus 6 bit error rate in about a day of computation. So it takes you a while to get to where the people thought the noise floors were around 10 to the minus 12 or so. So it takes thousands of days on workstations. NEC was the first one to try to do it on a cluster. I think this was the Earth simulator they did this on. So they did it and wrote this paper that describes the computation. And they ran out of time after whatever their time was on the Earth simulator. And they didn't see any noise floor going down to 10 to the 11th. Bora Nikolic and his students in our lab programmed this up on a B, and within a day, they processed 10 to the 15th bit, which was enough to get them and see the noise floor, the change in the slope of this at around 10 to the minus 12. So it's kind of supercomputer performance in this little platform. And it's curious that there's a few applications that work extraordinarily well on these FPGA platforms. Yes?
Doesn't the right-hand simulation run on something twice as big as the left-hand one? You have the numbers.
What?
Different. 2048 versus 1024.
Oh, you're right. Yeah, it's a different. Sorry, I'll have to ask Bora about that. I hadn't noticed that. It's a bigger code. Maybe I think that would be harder, but just my guess. Yep. Okay, so I'm going to we got about a couple more minutes. Okay, so the other set of applications that work really well are we've been working with the radio astronomers to build big radio telescopes out of lots of small dishes. There's a massive amount of signal processing associated with this. A lot of it is low precision, 4-bit data, maps extraordinarily well to FPGAs. That's a picture of an antenna installation that I took up in Hat Creek, California, that they're putting together the Allen telescope array, which you might know about. If you know Paul Allen, you probably do. One thing we built for them is a billion-channel spectrometer that they use for their SETI research. A single B2 board, 0.7 hertz channels over at 800 megahertz range. One B2 module gets about 333 gigaops at 150 watts. And it's actually installed doing sky surveys down in Barstow, California, in the high-tech packaging, that piece of 3/4-inch plywood. And I'm going to then. So here's just a quick list of. There's lots of users now. It's being used for all kinds of things. Some of those I mentioned: speech research at CMU, some bioinformatics stuff, of course, signal processing, DARPA and DoD contractors. And one thing we just launched about a month ago within the GSRC is a B2 initiative. So with special funding from DARPA, we've made available hardware platforms and help to a variety of the GSRC researchers. We asked for people to send in little white paper proposals. We just had a workshop with them last week, and there's a number of very exciting projects that are starting up with some great people, including Todd, who was here, and Wen Mei at Illinois, Mark Horowitz, and Kozarakis at Stanford. So we're looking forward to working with these folks and having them help us kind of build this infrastructure. And we're putting it all together in a common design repository where we're putting all our tools and software and documentation reference designs and helping the community. So that's all I wanted to say. Thank you.